Hello, my name is Brian Chaplin from the University of Illinois at Chicago, and the purpose of this video is to give an overview of a technology we are developing in our labs known as reactive electrochemical membranes. And I'm going to describe this technology and its application for the destruction of munition constituents and insensitive high explosives in manufacturing wastewaters. So I'll give an overview of the compounds that are present in these wastewaters, as well as our technology and how we're going to address destroying these compounds.
So I just want to spend a couple minutes and discuss the wastewaters that are produced during the manufacturing of these munition constituents. And we have a wastewater stream that's generated from the manufacturing process, and we also have another waste stream that's generated when these munitions are loaded into the various ammunitions that they'll be used for. And this is known as the load, assembly, pack operations. So both of these processes generate waste streams. The manufacturing process of the munitions is going to produce mainly wastewaters containing the organic munition constituents and also some inorganic oxyanions like nitrate that are used for the manufacturing process. The LAP operations, when we take these munitions and we pack them into the different ammunitions, these are going to produce a lower volume waste stream that contains these munitions and also some other species like perchlorate that is used as a propellant in these munitions. And so these waste streams are treated in different ways. So generally the LAP facilities are going to utilize absorbent-based treatment strategies, and the manufacturing wastewaters are going to use anaerobic biological treatment. But many times a treatment train is used where a combination of biological treatment and absorbents are used to treat this wastewater so it can be recycled and reused. The manufacture of the insensitive high explosives has made treatment more difficult because these compounds are more water soluble, so they're less amenable to absorptive treatment, and they've also shown to be very recalcitrant in some cases. So the traditional aerobic, anaerobic biological treatment processes do not work very effectively on them. Additionally, with these absorbent-based strategies, there is going to be a residual contamination that needs to be dealt with, so there is some concern over how to manage these residuals. There are various compounds of concern that are present in these wastewaters. I have their chemical structures shown on the left for a few that we are studying, and these are broken down into different categories. So the first category is our legacy munition constituents, and this comprises things such as TNT, RDX, and HMX, and these are traditionally treated by biodegradation and carbon absorption. We have a second category known as insensitive high explosives, or IHEs, and these are compounds such as NTO, DNAN, and NQ. And these were created because they're more stable to both heat and shock waves, so accidental detonation can be greatly reduced with these IHEs. And the problem associated with these IHEs in the wastewaters is that they are more water soluble, they're present in much higher concentrations, they're not as amenable to treat by carbon absorption, and they have also been shown to be very recalcitrant in some cases to traditional destructive treatment technologies. And in addition to these compounds, we also have toxic oxyanions that will be present. And so perchlorate is present because it's used as a propellant, and it's present in a lot of these LAP facilities. Nitrate's present in the manufacturing wastewater, and both of these compounds can typically be treated by biodegradation or ion exchange, although there's some issues with biodegradation of these compounds, and ion exchange will produce a concentrated stream of these. So really the goal of our work here is to find a treatment strategy where we can treat combinations of these organic constituents, be it legacy munitions, IHEs, and also at the same time that they're present with these toxic oxyanions. So the compounds that we're studying in our work here are shown on the left once again, and we have the different treatment goals associated with these compounds as well. It is generally accepted that a treatment train approach will be needed to treat these. So that brings me to the overall objective of our work, and that is to develop a single destructive technology that can remove both the organic constituents as well as toxic oxyanions that are present in the wastewater. And so we're going to accomplish that through electrochemistry and the development of electrocatalysts for these specific contaminant removals. And we're going to leverage our existing work on developing reactive electrochemical membranes, or REMs, that we've been doing for several years in our lab, and place these electrocatalysts on these membranes to accomplish our treatment goal. And so we have a schematic of our REM shown on this slide, and we have concentric tubular membranes. One of them serves as our anode, the other one serves as our cathode. These are microporous in size, so they have about 1 micron size pores. So nominally they're going to be close to microfiltration. But we can polarize those, we can place electrocatalysts on these membranes and accomplish specific electrochemical conversions. So the way we conceive this working is we first pass our contaminated water through our anode, where we can oxidize our organic munition constituents to nitrate, CO2, and water. Then the water passes through a porous cathode, where we can electrochemically reduce nitrate and perchlorate that's either already present in the stream or that's generated on the anode itself. And the goal here is to have a one technology that can remove all of these compounds. One of the keys to the performance of the REMs is related to its mode of operation.
So now I'm going to discuss how we make these membranes. So we start with a TiO2 ceramic membrane, which is shown on the picture in the bottom left at the top. And we convert that to what's known as Ti4O7. So I'm showing the overall reaction there. We have TiO2, we add hydrogen gas at a very high temperature, over 1,000 degrees Celsius. That is taking some of the oxygen out of TiO2 and combining with the hydrogen to form water. And now what we have is known as a suboxide of TiO2 with a nominal formula of Ti4O7. You can see from the image at the bottom on the left that the color of the membrane changes from a whitish beige to a bluish black, and that also imparts very high electrical conductivity to the material. So now if we look at the picture in the center of the image, we can see how we were actually operating this. So we have our tubular membrane, which we're operating as what's known as an anode to form oxidation. We put a stainless steel rod in the middle, that's going to be our cathode. We flow water inside that membrane, and we then force it by pressure through the pores. So the image on the far right is showing a schematic of these pores, and we can think of these pores as a collection of microreactors, and we can take advantage of all the internal surface area of those pores, and many times we can get very high conversion of a compound by just passing it through our membrane a single time. So what does this actually look like in a real treatment process? So what I'm showing in this image is what's known as a multi-stage operation. So we have 3 of these membranes operated one after another, otherwise known as operation in series. And so the image is showing that we're pumping our water, our wastewater, through the center of the first membrane, and we're recirculating that. A portion of that wastewater is going to go through the pores, and that's going to enter into the second membrane in this stage. So every stage that we go through, we remove more and more of the contaminants. And we may need 1 stage, we may need 2, 3, or even more to meet a treatment objective. So that's the beauty of this technology, is it can be operated as a modular unit. So we can add as many as we need in series, as shown here. We can also add a lot of these in parallel. And this depends on the total volume of wastewater we're trying to treat, as well as the treatment objective. And all of these membrane units, these REMs, are powered by DC power supply. So we can control the current or voltage that we apply to these membranes in order to fine-tune these for a given treatment objective.
So here we have an image of the experimental setup that we're using in the lab to test this technology. So this represents a single stage. We have our pump that's going to circulate the water through the center of the membrane. We have our potentiostat, which is shown at the bottom right. This controls the potential and currents. We have, of course, our tubular REM, which is the black membrane in the center of the image. We have our counter electrode, which is a stainless steel rod that runs through the center of that membrane. And we also have our back pressure regulator. So this is operating cross-flow mode. We run the solution through the center, circulating that solution. A portion of that liquid is coming through the membrane pores, and that's known as the permeate. So we measure that over time to see the amount of contaminants that we are removing. So this is our overall experimental setup, and we're testing this technology, and hopefully we can apply this for the degradation of munitions wastewaters.